Good morning and good evening, everyone. Thank you for joining us for our webinar, Scoring for PD-L1 using an AI-based digital pathology toolset from OptraSCAN. We're going to get started in just a minute, but just a couple housekeeping things before we begin. We will be sending out copies of the presentation following the webinar, so please feel free to sit back and relax and listen to the presenters. We will also be taking questions throughout the webinar, but holding on to them until the end. So please don't think that we have not received your question. We'll just be holding on that onto the end of our presentation. So first, a quick introduction to our presenters. Dr. Clive Taylor, Consulting Chief Medical Officer at OptraSCAN, attended medical school at the University of Cambridge and completed his doctoral studies in immunology at Oxford prior to accepting an appointment at University of Southern California, where he served as chair of the Department of Pathology and Laboratory Medicine for 25 years and was dean for educational affairs for 10 years. In addition to Dr. Taylor, we have Dr. Anagha, who is a medical graduate and postgraduate in pathology from well-reputed BJ Medical College in Pune, India. After gaining extensive experience in clinical pathology for over 12 years at Bharati Vidyapeeth University Medical College, Dr. Jadhav forayed into the field of healthcare IT at OptraSCAN, where she applies domain expertise to innovative imaging systems. And a quick introduction to our topic. There is evidence that the efficiency and accuracy, reproducibility of pathologic diagnosis can be enhanced by digital technologies and AI tools to assist the pathologist. In this webinar, we'll present an AI-based tool set for the automated scoring of immunohistochemistry slides for assessment of programmed death-ligand 1, PD-L1, expression in non-small cell lung cancer. And now we'll turn it over to Dr. Taylor.
Good morning, afternoon, evening, depending where you may find yourself right now. I welcome the opportunity to talk a little bit about PD-L1, the difficulties that pathologists encounter in achieving accurate and reproducible scoring, and the possible value of using AI-based algorithms to improve the situation. I shall give some general background to PD-L1 and PD-L1 scoring, and then Dr. Jadhav will describe the details of a recent research study using the OptraSCAN system and 3 pathologists to look at PD-L1. Sorry, I'm having problems moving the slides here. So I have consulted with a number of companies in the field, and from them I have learned much. So my thanks to them, and obviously to OptraSCAN as the sponsor of this presentation. I have to emphasize, however, that all of the opinions presented are my own alone. So we're in the era of precision medicine, and it obviously requires precision diagnosis. It turns out that many of the targets for personalized therapy are in fact proteins, and in theory, immunohistochemistry should be the ideal method for the detection and measurement. The fact that we have difficulties relates in part to assay performance and choice of controls, which need to be improved, and that's a separate topic, but in part also to the need for better interpretation and reproducibility of the scoring results. And that, of course, is the topic for today. The underlying theme of all of this is that pathology diagnosis is technology-driven. 180 years ago, the microscope changed everything in medicine, and in fact, you could argue that it actually invented all of us who are anatomic pathologists, because we had to learn how to use this new technology, and so pathology was born in that context. Today, we're in an era of comparable change of a probably greater magnitude, where there are 2 technologies driving this. One is the advent of molecular genetic methods and the ability to demonstrate molecular changes in a tissue section environment. And secondly is the rapidly accelerating development of digital computer analysis. Put those 2 together, and it will change pathology, I believe, into the age of the intelligent microscope. We've reviewed a lot of this in a book called Magic to Molecules, with Jan van den Tuyl as the primary editor, that was published a couple of years ago. So the age of the microscope was about 150 years old. Diagnosis was by H&E, and image analysis did occur, of course, but it occurred by mind and by microscope, and all of the great names that we learned about as we learned pathology, Cahal, Weigert, Maximov, they in fact were applying image analysis to the microscope using individual minds, and getting reproducibility amongst two individual minds can be difficult. It did, however, lead to the H&E becoming the gold standard for cancer diagnosis, and it still is today, supplemented to some extent by 40 years of immunohistochemistry. But we should remember that we've used immunohistochemistry in that 40 years, by and large, as a special stain. In fact, a whole range of 200 or 300 special stains. And now suddenly things changed. The change occurred about 20 years ago. The first companion diagnostic was approved by the FDA on September 25th, 1998, when they wrote a letter to DACO, as it was then, approving the Hercept test, which was approved in a clinical trial in conjunction with approval of Genentech's companion or corresponding drug, Hercept. About the same time, radiology went digital. And this was, again, technology-driven as the cameras used went to digital mode. And at that time, it became clear that digital pathology was going to develop, and studies began to appear over the next couple of decades, validating whole slide images for diagnostic purposes. And in fact, there is now an approved whole slide image system from Philips for that purpose. So let's touch on companion diagnostics, because PD-L1 falls into that arena. Companion diagnostics, as I've alluded to, are approved in clinical trials that involve a trial in conjunction with the specified targeted therapy, and the two are approved together in concert for predicting responses to the targeted therapy. These sometimes are known as predictive biomarkers, advanced personalized diagnostics, precision diagnostics, etc. Many of the approved ones turn out to use immunohistochemistry, so that will be our topic today. Approval, of course, is required for clinical use, and approval includes the assay itself and the scoring method. Change any part of the assay or any aspect of the scoring method, and you no longer have an approved test. Lab-developed tests form a second pathway for us as pathologists to use these types of tests, but they do require extensive validation, and I'm going to get into that in a moment. So how do we do this, and how many companion diagnostics will we need? The underlying scientific background really goes back to many researchers in the 90s, prominent among which were Bert Vogelstein and his group. And this is a very nice summary paper in Science from Vogelstein in 2013. The concept really is that cancers are multi-hit processes where a series of sequential hits occur, altering genes either by mutation, deletion, or methylation changes, and that changes protein expression. It means that different tumors, in this case illustrated by colon cancers, although they may look similar or identical histologically, may in fact do have different mutated driver genes, 4, 5, 6, or 7 driver genes, and that therefore produces different expressions of molecules on the surface of these cells. The pie chart shows some of the molecules expressed in colon cancer, and the challenge then for pathology is to inform the clinician which of these molecules are expressed or hyper-expressed, such that the targeted therapy, if available, can be applied. So we use companion diagnostics to target these molecules. How do we do that? Well, basically any way we can. Whichever method works most effectively, whichever method we actually have in the lab, and whichever method we can actually afford and validate. I'm going to confine my comments today primarily to immunohistochemistry. This advent of companion diagnostics and this new modality for immunohistochemistry already has radically changed pathology. The little pie chart at top left, 10 years ago, a decade ago, as short a time as that, we were very happy if we could train our residents to distinguish 4 types of lung cancer, small cell and 3 types of non-small cell, with the aid of some immunohistochemistry stains. Today, that's not adequate. Give that information to your clinician, they won't be satisfied. Their next question will be, okay, that's well enough, but I need to know which proteins are expressed and which of these proteins are available for me to use in relationship to one of the armamentarium of targeted therapies that I have. Is it KRAS or is it HER2 or EGFR? And that cannot be determined on H&E alone. So in this context, we're talking about applying immunohistochemical stains for HER2 or BRAF or KRAS or ALK or MET or whatever molecule your clinicians are interested in with respect to their available approved targeted therapy. There's an additional layer of complexity then as immune blockade inhibitors appear in the form of PD-1, PD-L1, and I'll move on to discussing that in a little more detail. So these various proteins that are hyperexpressed work in various ways in relationship to the cancer process. They can assist the immune system to destroy cancer cells, or they can block that process, or they can induce cancer cells to undergo apoptosis. We have to be able to detect which of these are present in the tumor in a validated method in the lab. And how many of these tests could we need? Well, there are at least 80 or so targeted drugs in various stages of approval or in clinical trials. And many, not all, but many of these could require companion or complementary diagnostics that we as pathologists would be asked to perform. The PD-L1, PD-1 axis, if PD-L1 and PD-1 are bound, the two ligands are bound, then while a killer T cell may bind to the tumor cell through antigens present on the tumor cell, killing will be inhibited. If we have an antibody to PD-1 or PD-L1 shown at top right, it will break this ligand pairing and then will allow killing, but only, of course, if CD8 cells are present. Now, the complexity of this process is that the pharmaceutical industry has been incredibly innovative, and there are many different PD-1 or PD-L1 inhibitor drugs available. This chart just shows 5 of them, and it also shows 8 or 9 different tumors in which intervention with these targeted therapies has been shown to have some clinical benefit. Now, it's important to grasp that when one of these companion diagnostics is approved, let's say for Pembro or for Nivo, it can only be used for that particular drug. It cannot be extended to use for any of the other drugs. And in addition, it can only be used, generally speaking, for that particular tumor in which the approval process was derived in a clinical trial, and cannot be extended to another tumor. Put it another way, in a simple term with an older test like HER2 for breast, the actual scoring mechanism does not apply in the same manner to HER2 for gastric. So that produces a really complicated problem for pathologists. We're being asked to tell the clinicians which patients will respond by a test and by a test alone, and which will not. And yet we probably need to develop many different targeted therapies and many different companion diagnostics to do this. If the clinicians wanted to use any 3 of these 5 drugs on any 3 of these 9 tumors, we've got at least 9 different tests that we would have to set up to do that. 9 different tests requiring different antibodies, different platforms, different scoring mechanisms, none of which are translatable one to another. So one way around that it has evolved that labs are beginning to use lab-developed tests. This is a mechanism, of course, that has been there for years. Call them home brew, if you will. And I'll get back to home brews in a moment. So an approved class 3 IHC test. FDA approves these in the US. There are different approval methods in other countries. This is one such test, one of the first actually that came out of Dako Agilent. I happen to be involved in that process. And if we just look at that test, in one way, it's essentially a highly validated, ready-to-use test, FDA approved in conjunction with a clinical trial using the specified companion targeted therapy. The method is rigorously validated. The primary antibody is rigorously validated. The automated detection system, it's an automated platform, is validated. The control system is validated, and the scoring method is validated. In this instance, it's a manual scoring method. If a digital algorithm was to be used, then that also would have to be validated. including the scanning platform and the software. And each of those validated approvals would be specific only for that companion diagnostic and that specified companion drug. LDTs are currently not regulated by FDA directly, but FDA has expressed interest in the past in doing so. But even with the lack of FDA regulation, the rigor of validation of a lab-developed test is increasing. So it's not easy to validate a lab-developed test for PD-L1, for example. And in fact, in my opinion, it's beyond the capability of most laboratories to do that. Here's a slide courtesy of Suzanne Parry, who's at UK NECAS. UK NECAS is the United Kingdom National External Quality Assurance System. It works across many different areas of technology, but in labs, it's a way of looking at immunohistochemistry. And this chart shows 4 different drugs, and it shows 4 different vendors. It shows 4 different monoclonal antibodies and 2 different platforms. So to do any of these tests as an approved diagnostic, one would have to set up each one of those separately and validate each separately. In passing, one of these, the DACO22C3 on the right, is a companion diagnostic. Its use is required to give the drug. The other 3 are complementary diagnostics, meaning that the correlation perhaps is not quite so tight, and it's recommended that they're used before use of the drug, but the requirement, in my understanding, is not absolute. So, in this survey and in surveys by Nordic QC, what was really interesting was that in surveying labs, only about half of the labs were in fact using an approved companion diagnostic or complementary diagnostic. The others were using lab-developed tests that they had developed themselves. And the correlation of reproducibility amongst the lab-developed tests was less than for the approved diagnostics, not surprisingly. However, Nordic QC in a separate study showed that with the 22C3 antibody run now on 4 different platforms from 3 different vendors, you can in fact achieve reproducibility of tests in a lab-developed test modality. Green shows high positivity, yellow shows low positivity, and red is negative. And you can see they can be very similar in spite of the fact that the actual immunohistochemical stain shown in the boxes on the right looks rather different. Once you establish the different scoring methods for those different stains and the intensity of those stains, you can in fact correlate the results. And this was done by scoring scanned slides. So it is possible to coordinate and cross-validate these, but it requires an enormous amount of work to do that. And as I've said, it's beyond the capability of many labs. So let's look at the PD-L1 problem to try to understand how artificial intelligence and whole slide imaging might be of assistance to the pathologist. It's not replacing the pathologist, but it may assist us in interpretation. Many different antibodies, many different approved tests, and the scoring systems are complex. They're different for each test. You have to decide what the threshold is for an individual cell to be positive, how much membrane's got to be positive, how intense should it be. You have to figure out the percentage of positive cells in one mode or another. It's semi-quantitative at best, and some assays require other difficult tasks, such as the presence and/or location and/or positivity of associated immune cells. We should have a scoring system that's reproducible. At present, we clearly do not. Then a new dimension was added, really began in melanoma, a paper here by Toomey and Taylor about 4 years ago. They looked at a series of melanoma patients treated by immune blockade inhibitors and rebiopsied the cases after 4 to 6 weeks. If you look at the upper left box, those patients responded to therapy, and all the brown dots are CD8 positive killer T cells. And after therapy, the second box in the upper right shows that in fact there are many more CD8 cells after therapy. Those patients responded, as you can see on the right. The 2 bottom boxes show patients that did not respond. There were very few CD8 killer T cells present before therapy, and they did not accumulate during therapy. And only one of those patients, in fact, showed a response. So this was very powerful evidence that not only did we need to know whether the PD-L1 was expressed, we also needed to know whether there were immune cells sitting in the background ready to be released from suppression. Tissue extraction methods can give us inferential information, NGS, PCR, RNA expression, proteomics, but they only give us an inference that an immune response may or may not be present. Multiplex immunohistochemistry, or bright field in some contexts, can give us more precise information of the relationship, one, of the tumor cells to the immune cells, and two, whether the immune cells are in fact present at all. So this has spawned a whole series of summit conferences, so-called summits. I've been to a few of these. I'm aware of at least 20 in the last 3 or 4 years, and there must be at least that number of which I am unaware. The notion is that there are 2 categories of cancer, and those 2 categories are immunogenic or inflamed, in which there are immune cells present. The tumor has neoantigens, but the immune cells are not functioning because there is a PD-L1 type blockade, and the treatment then is to block that blockade. Opposed to other tumor types which are silent, there are very few neoantigens, there is no immune response, and even if you give a PD-L1 inhibitor under those circumstances, nothing will happen because there are no CD8 killer cells in the background. So we can find these immune cells elegantly by using multiplex immunohistochemistry, sometimes in combination with FISH. We can look for the ligand pair like PD-1 or PD-L1 or both, and we can look for the immune cell phenotypes such as CD4, CD8, CD68, FOXP1 for activated T cells. So that's a multiplex stain, 4, 5, or 6 stains or whatever, all performed and visualized simultaneously. So that produces really excellent studies that actually are spectacular. This is a study from last year, PD-1 blockade and pembro treatment in Merkel cell carcinoma. Merkel cell carcinoma, of course, has a viral background and tends to have a strong immune response. If you look at the left window at the bottom, you can see all the green and white coloration represents PD-1 and PD-L1. The orange represents the tumor, and the little yellow circles are the CD8 killer T cells. Look at the rebiopsy after 3 weeks of treatment on the right. You can see there's now very few orange tumor cells left. The amount of PD-1, PD-L1 has been reduced, but there are many more CD8 T cells, and at the top window, clinically, the tumor shows regression. So these studies are very elegant in their research mode. The problem is that there is no multiplex FDA-approved test, and it will take a while to get that done if it is done. The methodology and the equipment is relatively expensive and not available in most labs. It's relatively slow and requires expertise in getting it up and running. Once it's running, it's fantastic, and you can spend all day looking at these things. It is relatively expensive in relationship to a double or triple stain, but I should point out, in fact will point out, that it's still only a fraction of NGS. It's less than $1,000 versus more than $5,000, and it can be done in a couple of 3 days as opposed to a couple of weeks. So there are huge advantages of this methodology. But let's go back to what faces us as pathologists. Here's a typical DAB brown stain PD-L1 IHC. We're asked, is this 0 or is it 1%, 5%, 50%? To be negative or positive, which one of these 4 would you treat or not? And it's a difficult issue. Is the top right quadrant field, is that 1% or is it 5%? Top left, 1%, 5%. Bottom right, 48% or 52%. Well, we don't usually bother about 48 versus 52, but if the threshold is above 50, is it above 50? It's a guess. 1 and 5 are the important numbers, generally speaking, because of clinical studies. The left-hand boxes show PD-L1 of greater than 1%, and you can see that the curve for the patients with a greater than 1% expression is better than for those with less than PD-1. And then the boxes on the right, PD-L1, 5%, and even greater divergence. So those are the magic numbers that we tend to go for. So now let's look at a slide and analyze what we as pathologists are being asked to do, and in fact, what we are cheerfully doing. If we're going to give a percentage, 1%, 5, 10, 50, whatever it is, we need to know the number of positive cancer cells and the total number of cancer cells, and we divide them. tissue section, such as this one, which is relatively large, we can do the math and work out how many cancer cells could be present. And if we just do pi r squared with tumor cells at 20 microns in diameter, there can be up to 2 million tumor cells in this tissue section. This is not all cancer, it's partly cancer, so you have to estimate which part is cancer. We don't count the whole section or even try to. Of course, we can't. So we tend to do a field. And here's a times 4 field, here's a times 10, here's a times 20, and here's a times 40. So a times 10 field, again, by mathematics alone, can have up to 10,000 cancer cells, and a times 40 field can have 600 cancer cells if they're each 20 microns in diameter and if they're shoulder to shoulder. Of course, it varies with cell size and mix of tumor versus stroma. We give a number, but we really guess. It's remarkable that we can guess so closely if we train ourselves. But my contention is that AI and whole slide imaging can make us better. So let's look at one specific advantage example. If the threshold here is 5%, is this patient going to get treatment or not? One high power field, we're going to do a tumor proportion or percentage score. So we need to know how many cancer cells are present. That's the denominator. We can't count them all in this field. We could try, but we really can't. So let's say about half the field is cancer, and let's say therefore it's about 300. So that's going to go below the line. We now need to know the numerator above the line. So this is where it gets to be interesting. If there are 15 cells, we've hit the threshold. So 15 cells positive gets $100,000 worth of treatment, 14 does not. Anybody think they can do that reliably? I know I can't. I mean, I've tried. It can't be done. So we finish up looking at lots of fields and we come up with a consensual personal opinion as to what we think the answer is. And it's difficult to do that. And it's even more difficult because the denominator we might have gotten wrong too. If it's 330 and not 300 or 270 and not 300, then the numbers of course change. And even if we do that in one field, we've only scored a minute fraction of 1% of the whole tumor. So this is a huge challenge that we've coped with in a practical sense quite well, but we could be better. And there's a second problem. As pathologists, clinicians think, and we perhaps don't disabuse them, that we can easily distinguish cancer cells from other cell types like macrophages. I have convinced myself that we cannot do that in this context on a cell-for-cell basis. We can do it amongst populations, but not individual cells. So at the top, this is an adeno-CA stained for PD-L1. How many positive cancer cells are there? 96, 127, 150? It's hard to tell. We certainly can't count them. And we would be wrong if we did count them, because if we do a second stain, in this case for CD68 for macrophages, we can see that about 40% of the positively PD-L1 stained cells, in fact, are not cancer cells at all, but are macrophages. And if we look on an individual cell-to-cell basis, going back to the PD-L1 stained slide, there are cells there that are indistinguishable on a cell-to-cell basis, tumor cell versus macrophage. And only a double stain sorts that out. That's the advantage of multiplex, of course, which we cannot at this point routinely do, and for which there are no approved tests at this point. Look at the bottom, the squamous cell carcinoma. Does that exceed 1% for a positive result to get treated, or 5%? Most pathologists I showed this to scored it above 5%, and certainly above, all scored it above 1%. But if we do now a double stain again, where we stain the tumor cell nuclei red for P63, this is a squamous cancer, we can see there's not, in fact, even one positive cell that has a red nucleus. So this tumor, in fact, is totally negative for PD-L1, although all pathologists scored it as above 1%. And then we've got a way of dealing with this has been to propose a so-called CPS score, a combined positive score, where above the line now you put all positive cells. That's positive tumor cells, positive macrophages, positive lymphocytes, and divide by the total cancer cells. In some ways it makes it easier, but it makes the counting even more difficult in some respects. And then we have heterogeneity. We can have 3 plus 2 plus 1 plus in the same field for HER2, shown here, and the same thing can apply with PD-L1. And that's also very difficult to evaluate in a manual analytic process. And then when you come to immune cells, we have a further problem of the irregular or heterogeneous distribution of immune cells. They can be just around the margin of the tumor, as you can see, or they can be infiltrated throughout the tumor in irregular fashion, which may or may not relate to the PD-L1 distribution, as you can see in the bottom two boxes. And we're then charged with deciding whether the PD-L1 is on the tumor cells or not on the tumor cells and doing a score. It is very, very difficult. And then the last issue that I'll touch on before I hand over to Dr. Jadhav is that we obviously don't count the whole section. We can't do it even if we try to use the old hemocytometer method of counting cells in a blood film and a clicker. It's just not possible to do it. We would need a grid to do it. So we tend to pick out separate fields, and we score n fields, where n might be 5 or 10, at times 10 or times 20 or times 40, and we get an average across those fields, and that's the number we write down. But clearly, as shown in this slide, the number you actually finish up writing down depends on which fields you pick. You could pick 5 fields here that would give you a score above 1 or 5%, and you could equally pick 5 fields that would give you a negative score, and it's the same piece of tissue. So field selection is a huge bias in manual scoring, but it's also a bias in many AI or image analysis algorithmic approaches, which require the pathologist to choose the 5 fields, and the algorithm then looks at the fields that the pathologist has chosen, whether it be at 5 or 10. So the selectivity and the subjectivity of selection still has a huge effect on the diagnosis, even with those algorithms. So an algorithm to abolish that would need to look at the whole slide section. So this is what the goal was of the study that Dr. Jadhav will describe. The algorithm was based on a whole slide image to avoid the bias of field selection and to allow for heterogeneity of PD-L1 expression. And it also looked at immune cell distribution, and it was also to accommodate the uneven distribution of immune cells. The method was coupled with deep machine learning approach, such that as pathologists, 3 pathologists came to a consensus scoring on images, then the algorithm relooked at those images until its scores basically stabilized. And that method was then, in a training set, was then adapted to the algorithm, which was then compared with the pathologist. A tool like this will not replace the pathologist, but it can be used as a valuable learning tool for pathologists to look at your manual score versus the machine to see if you're close to the machine, and also as a confirmation tool for whatever the manual score might be. And it provides assistance in interpreting new and difficult assays. So I thank OptraSCAN for the opportunity to provide this brief presentation. My view of what the microscope will look like in a decade is not like the upper left-hand corner. That's an antique. You will still keep one for a few of the cases, but it's going to look more like the screen on the right, which is an iPad or whatever it is, where you will just click on the app for the appropriate information that you want to help support your visual interpretation of the slide. With that, this is the study that we've been working on, and I will pass the microphone and the screen across to Dr. Jadhav. Thank you very much.
Thank you, Dr. Taylor. That was really helpful. So I'll walk you through the validation study and the algorithm training and implementation. The main purpose of this study was to validate and assess the reproducibility of Optra automated PD-L1 image analysis solution for non-small cell lung cancer. The cohort consisted of immunohistochemistry slides that have been stained with the FDA-approved PD-L1 IHC with anti-PD-L1 22C3 mouse monoclonal primary antibody, and the slides were obtained from the archives. These slides represented 230 cases of non-small cell lung cancer. There were additional training sets and evaluation sets of slides, which included TMAs, tissue microarrays, and they contained the representative lung cases with variable PD-L1 expression, which were utilized for training and validation of algorithm thresholds. All the slides were stained that were at 5 micrometer sections. They were stained using the antibody mentioned, and they were scanned with OptraSCAN at 20x magnification with resolution of 0.5 microns per pixel. 3 board-certified pathologists, including Dr. Clive, Dr. Jadhav, and Dr. David Rim, from different institutes across the United States, and all with extensive recent experience in interpreting the assay, independently recorded the percentages of tumor and immune cell staining positively based on the scoring guidelines. And these were the scoring guidelines. There are 6 score categories for tumor staining and 3 score categories for immune cell staining. A subset of cases which were representative of the entire cohort was selected to render the study more feasible for the participating pathologists in order to compare interpathology scores and to validate automated scores generated for tumor and immune cells. Now, in order to select a representative sample of 100 cases, which was calculated from the sample size calculation, all the cases were stratified, which were the 230 lung cancer cases, into previously described NCCN score categories, and the following analytical components were assessed. The tumor cell staining, which was an estimate of percentage of tumor cells exhibiting either partial or complete membrane staining, and immune cell staining, which was an estimate of the percentage of immune cells, which included the macrophages and lymphocytes within the tumor exhibiting staining. The staining was based upon the entire slide. The digital images were rendered viewable using the Optra web-based image management system for viewing and recording individual whole slide image scores. All images were hosted on a dedicated server with a user login for individual pathologists. Now I'll walk you through how the training and the evaluation of a robust PD-L1 algorithm was developed using feedback machine learning process. So for development of Optra membrane algorithm for PD-L1, the training data set consisted of 40 whole slide images using the antibody mention, which accounted for a rich variation in tumor and immune cell positivity for lung cancer. Whole slide tissue images usually consist of 30 to 800 fields of view, and each field of view, as can be seen on the top right corner, were the input images for the training of the algorithm. To be sure we did not miss on hotspots for tumor and immune cells, negative tumor or immune cell membrane positivity and density of immune cells, we subjectively selected fields of view from this set of whole slide images to represent a variation in intensity and percent positivity for tumor and immune cells. Now the following parameters were assessed after further training and quantification was done. So the quantification was total number of tumor cells with positive and negative membrane staining, total number of immune cell staining which showed positive and negative membrane staining, total number of tumor cells with membrane staining, and total number of immune cells with membrane staining, as can be seen in the overlay, and I'll walk you through later with that. Further refinement of the algorithm was done, and the training continued, followed by iterations of training and evaluation sessions by a board-certified pathologist who was also experienced in scoring PD-L1 antibody stain for the assay used. Post-training iterations, a validation set 1 comprising of 50 whole slide images, which were not a part of the training set, were run for implementation of the fully trained robust algorithm. ROC curves were plotted to assess the performance of the algorithm at 1% cutoff for both tumor and immune cell positivity at any intensity. Here we can see in the ROC curve that the algorithm performed well with AUC of 0.8 for tumor cells and 0.7 for immune cells. The fully developed, quantitative, robust PD-L1 algorithm was then implemented on each whole slide image of validation set 2 to generate an automated whole slide percent positive membrane score to generate separate scores for tumor and immune cells according to the pre-selected cutoffs for the above mentioned standard PD-L1 assay without any human intervention. So here was how the images were rendered viewable, and this can be integrated into the lab information management system. Here is a login for the pathologist, a typical pathologist dashboard wherein you can see which all cases are being assigned, which are closed, which are referred, and which are yet to be resolved. Here is a typical case set which a pathologist can see on his dashboard on clicking an individual cell. For the case, the slide opens or the image opens in an image viewer. One can just analyze using the appropriate algorithm assay. So here one can use the PD-L1 assay, and one can see that the image has been opened in the image viewer with a zoom in, zoom out capacity. After analysis, an overlay is created, and this is now a look on zooming, which can be zoomed up to a 20x and a 40x magnification. So this is the raw image. This is an analyzed image. So one can go back and forth to validate whether all cells have been picked up or not. And this is a very beautiful technology, as Dr. Taylor just mentioned, about the problems that a pathologist as human cannot count each and every cell individually, which can be done only with machine-based computer-aided technologies. So these are the parameters or the intensity values for both the nuclear and membrane staining, and for the morphological characteristics like the size, circularity, area, depending upon the cell size, and the intensity. So these are being rendered configurable for the user to account for subtle variations in hematoxylin content and the cell morphology. On the right side, you can see that the scores have been generated, and so can be seen in the overlay as well. And these scores can be exported in an Excel format. The statistical analysis was then computed with the computation of correlation coefficients ranging from 0 to 1, with 1 representing perfect reproducibility and 0 a poor reproducibility. For the pathologist's digital manual reads, in order to assess variability between the pathologies for scoring both tumor and immune cell positivity, or the percentage positive cell that has been scored manually, and also the correlation coefficients with assess concordance between pathologists' digital manual reads, and finally their correlation with the Optra PD-L1 image analysis scores for both tumor and immune cell separately. So these were the graphs that were being generated post the study readings. So the figure shows distribution of PD-L1 scores among the three pathologists and automated scores for individual cases, for tumor cells, for immune cells. These are for the total number of cases that were being scored by the pathologist as well as by the automated algorithm for the immune cells. Now, an interesting point that Dr. Taylor just highlighted, that FDA-approved cut points for the assay positivity are at greater than 50% and 1% for high expression and low expression respectively. Hence, it was very important variable for us to consider in the present study to determine comparison of pathologists and automated score concordances around these FDA-approved cut points at which clinicians prescribe drugs presently. So this figure illustrates the distribution of scores by each pathologist for tumor cells and immune cells in the slide to follow. The distribution of cases scored for tumor cell positivity above the assay specific threshold of more than 1% was 27 versus 72 for pathologist 1, 18 versus 81 for pathologist 2, and 19 versus 80 for pathologist 3. Immune cell score distribution observed around the cutoff of more than 1% was 20 versus 79 for pathologist 1, 7 versus 92 for pathologist 2, and 14 versus 85 for pathologist 3. Categorical scores among pathologists and with the automated scores can also be appreciated in a heat map format, as can be seen with the columns are the pathologist and automated scores, which have been sorted from A to N. Each box representing a pathologist and automated score for one case is color-coded according to the 6 tumor and 3 immune categories described previously. The Linz concordance correlation coefficient estimates between pathologists for tumor and immune cells, which range from 0 to 1, with 1 representing perfect reproducibility, were computed as described earlier. Pairwise concordance correlation coefficients between pathologists for PD-L1 expression in tumor cells showed a strong positive correlation. The CCC were 0.81, 0.78, and 0.68 between pathologists 1 and 3 2 and 3, and 1 and 2 respectively. However, the readings for immune cell scoring indicated a substantial discordance, as has been published in the previous studies also. It showed a discordance between pathologists, and we can see a high variation between the pathologists for scoring the immune cells. So the Linz concordance correlation coefficients for immune cells, as can be seen, were 0.5, 0.44, and 0.38 between pathologists 1 and 3, 2 and 3, and 1 and 2 respectively. Finally, the quantitative information computed by the algorithm was compared with the reads by the pathologist. The Linz concordance correlation coefficients between the conventional read and the machine scores were calculated for the comparison. The coefficients of concordance between the automated scores seen in the right column are 0.6 to 0.53 and 0.88 and 0.8 to 0.66 and 0.90 for tumor and immune cells. To compare the pathologist scores to the Optra automated system, the scores from the three pathologists were averaged to produce a single conventional read score. The Linz CCC between the conventional read and the machine score was 0.80 for tumor and 0.70 for immune cell population. So this is considered an excellent agreement for tumor cells and good concordance for immune cells. To summarize, the algorithm generated on a training set performed well on a validation set. The interpathologist concordance seen in this study is similar to the previously reported studies, where agreement is higher for evaluation of tumor cells than for immune cells, and that's where the algorithm in place. The present study shows that the Optra PD-L1 image analysis showed concordance with the pathology scores that were comparable to levels observed for interpathology scores of PD-L1 and tumor and immune cells. So this finding definitely suggests a promise for the use of automated whole slide image analysis assessment in non-small cell lung carcinomas for accurately generating scores for tumor and immune cell population. Over to you, Jennifer.
Great. Thank you, Dr. Jadhav. Thank you, Dr. Taylor. So now we're open up for questions, and we do have one here, so please keep them coming. So someone's asking about a copy of the intrapathologist concordance agreement available. Is that available anywhere?
So the publication is due, and it is under review by the experts, and it will be soon available.
Great, thank you. Some other questions. What challenges do you still foresee for PD-L1 despite the intervention of AI tools? And either Dr. Taylor or Dr. Jadhav, you can answer.
Approved assays, complementary or companion, or as an LDT, then getting a consistent, accurate, and reproducible scoring system among pathologists day to day, week to week for the same pathologist or across pathologists in the same institution, and particularly across pathologists at different institutions for the same test, is, in my experience, extremely difficult. I've been involved in training pathologists with several of the approved companion diagnostics, and it is possible with a group of pathologists, 3 or 4 or 5 pathologists with a training set and a testing set, to get pretty good concordance. Maintaining that level of concordance, however, in practice over 3, 4, 5 months is difficult. People tend to drift, and a second group will not have necessarily good concordance with the first group unless they are also trained in the same way. So this training process is vital, and one use I can see for an algorithmic approach like this up front is that it could provide a basis for pathologists to see how they're doing against a consensus method, because the algorithm developed in this study is in fact a consensus recognition for the pathologist, the 3 experienced pathologists who looked at these slides. And it's actually pretty good. It's as good as pathologist versus pathologist. So I can see that as one important method of moving forward. It's very hard to score one of these in a vacuum without knowing what how other people would have scored it. So I can see that as one upfront utility, and that's the way I personally use these types of algorithms.
Dr. Jadhav, anything from your end?
No, I think Dr. Taylor has made it very clear.
Great. Okay. And then in addition to that question, they also asked about improvements in AI tools. So do you foresee, or what do you foresee as improvements in AI tools specifically related to PD-L1?
Again, I'll give it first shot. My personal view is, and this is a personal opinion, it's not an opinion foisted on me by any of the companies I work with, including Optra. My personal opinion is that these complex types of immunohistochemical stains with multiple cell types cannot be reliably scored by manual visual means alone. There's no way of monitoring or maintaining or calibrating consistent performance. So I personally believe that these types of algorithms are going to be vital. I think the machine learning approach brings in parameters that the computer develops and uses that we don't fully understand at this point, but certainly are of assistance, and that's shown to be true in an H&E environment also, as well as in IHC. So this, I think the AI approach is going to be vital and will be an essential part of how we look at these slides in the future. How we get to the approval process here when we've got, as I've already described, 27 different tests out there is going to be difficult, and some way we need to find a solution to that problem.
Dr. Jadhav, anything from your end?
I'm good, Jen. So I would like to take up the second question that has come up. So when will the algorithm determine it has sufficient data, that is lack of continued variation, to stop additional analysis? So to answer this question, the algorithm presently developed was for non-small cell lung carcinoma. The parameters are exposed both for intensity of the stain of imidopsilin for that particular day and for the morphological characteristics like area, circularity, and so on. So presently it is very much robust for non-small cell lung cancer, though it will need a little bit of training if we consider other tumor types.
Great. And then we have another question for Dr. Taylor. What is the effective field size to investigate tumor microenvironment? Is field size down to 50, ROI overkill in investigation of immunological composition or drug?
Well, if I knew the answer to that, that's a good question, and it's a vital question. In my experience, across several tumor types, with immune cell infiltrates, I'm looking at them both visually, but particularly by multiplex IHC methods, is that the localization of the immune cell infiltrate is incredibly variable, both within a single case and certainly from case to case. And looking at a whole tissue section is vital. Just picking isolated fields, as a pathologist, even though I know I'm doing it, I gravitate towards selecting fields where there's a positive signal and away from fields where there's no signal. That's just the way human brains sort of work. So I'm sure I get biased analyses, whereas when you look at it with a computer approach, and there have been some excellent studies using the Perkin-Elmer multiplex system that have been performed by Bernie Fox up in Oregon, etc. You can actually come up with a percentage of tumor cells that have a killer T cell within 10 microns or within 20 microns. And that's the sort of information I think we have to have. Just saying there are some immune cells present, I think in the final analysis won't do it. They have to be in a contiguous situation such that if a blockade is released, they're in a position to affect and kill the tumor cells. And then lastly, although I'm talking about a whole slide image, we have to remember that a whole slide image still is a small selection of the whole tumor. And so we've got problems here, but whole slide images and whole single sections are what we base diagnosis on. And that's proved reliable over 150 years of H&E. So I personally believe you have to do this on a whole slide image.
Great. We have a couple more questions that have come in. So first, a double question. How are the tumor cell fields selected automatically? And the second part to that question is it still manually selected by pathologists based on H&E?
So Jen, I'll take up this question. Thanks for asking. And it was been included in the training and evaluation of the algorithm. The tumor areas can be selected both. There are two ways, two modalities by which analysis takes place. It can either be done manually by selected fields by a pathologist. It has also got an automated or an auto-analyze mode, wherein there is no need for any human intervention. So that answers the second question. For the answer to the previous question, how the tumor cells or fields were selected automatically, so that was that comprised the training and the evaluation of the algorithm during the development. So the modality that was used during development was a multi-phase intensity and morphology-based segmentation, which was completely automated for identification of all viable nucleated cells in the individual fields of view, and ultimately the whole slide image in both the planes. So the nuclear viable tumor cells were segmented in the blue plane of the input image based on the intensity values for hematoxylin counterstain, and the cells exhibiting membrane positivity were identified in the red plane of the input image. So everything happens automatically, and the cells are being segmented into nuclear and immune separately, and the scores are being generated to follow that.
So may I just add to that? This is a rapidly advancing, evolving area, and that you're probably aware, many of you, there is a study called the Chameleon study that's been going on for 3 or 4 years now, where they're looking at H&E only of lymph nodes with or without metastatic breast cancer, where there's a consensus pathology opinion as to whether metastases are present or not. And this study's been done, I think, a couple of times that I'm aware of. There's maybe a third time going on. And the computer-based machine learning algorithms came close to matching the pathologists first time around, but second time around they beat the pathologist. It's a bit like Big Blue beating Bobby Fischer or Boris Spassky or whatever it was at chess. Once it did it once, it could do it every time. So my personal view is that machine learning can identify morphologically tumor cells using some of the parameters that we as pathologists understand, but also learning to use other parameters that we just don't understand at all, but still coming up with an answer that's as good as or better than we can achieve. So supplementing Dr. Jadhav's answer, the computer, after a learning phase that she described, was able to identify the tumor cells with great reliability, as well as I could do it in these cases, and that's what the scoring was based on, without human intervention.
And one final question. Thank you, everyone, for supplying us some questions today. When will wide use of PD-L1 analysis be available for other cancer types, such as colon cancer?
I don't know the answer to that. I would know it won't be tomorrow. It will take a little bit of time.
Great.
Yes,
well, that looks like, are you going to go ahead, Dr. Jadhav?
Sorry, Jen. So post-validation.
Yeah,
so post-validation of PD-L1 analysis in lung cancer cases. Presently, we're validating in GI cancers as well. So not tomorrow, but yes, soon it'll be available.
Very good. Thank you both. Excellent content, very relevant and timely right now. If there's any other questions, please go ahead and email us at info@OptraSCAN.com. We will be sending a copy of both presentations out to everyone, as well as a link to the recording. The recording will also be available on our website at www.OptraSCAN.com. Thank you, everyone. We look forward to seeing you next time.
Thank you.
Thank you, everyone.
Bye-bye.